Hello everyone, my name is Karen Attree. I'm from Henry Wisewood High School in grade 11, and this is my Alginate solution for the Calgary Youth Science Fair. Alright, so to begin, I want to address the significant challenges that we face currently regarding healthcare inequality across the globe. It's becoming an increasing problem that people in impoverished countries are facing a larger and larger disparity, a larger and larger gap between us in the Western and wealthier countries, where they aren't able to access the kinds of healthcare and tools that we have, and are suffering and dying and as a result. So this project in particular, I wanted to focus on finding ways to reduce healthcare inequality. This is something that I am very, very passionate about. I believe that it is an inalienable human right for everyone to be able to have access to healthcare and to have access to the tools and methods that everyone else does. Everyone has the right to be healthy, in my opinion, and I believe that companies, and I'm not going to get too political, but I believe that companies tend to overprice things, and they don't necessarily look for the simpler methods. They tend to stick with what they've already seen, and this can lead to a lack of innovation in the areas of making things more accessible and more available to people who don't have a lot of money to spend on these materials. So my project in particular is focused on sutures and the development of dissolvable sutures. So I decided to focus on dissolvable sutures, for one, because commercially available dissolvable sutures are quite expensive as compared to regular sutures. Also, the fact that the dissolvable sutures are inside your body can reduce rates of infection. So obviously, if it's on the outside of your body, it's more prone to infection. Inside, it doesn't necessarily work, or it doesn't necessarily pose a problem. As long as the material used for the suture is biocompatible and non-immunogenic, you're going to be okay with the infection rate of things. And obviously, there's been a lot of deaths and a lot of disease and a lot of pain and hurt that's come from infections from sutures. So these are really unnecessary. I believe with dissolvable sutures, we can prevent a lot of this from happening, and we can have it inside the body, so it's not as much of a problem. Also, after doing this project, I looked into the actual application of it, and I realized that these sutures that I developed are probably best suited for cesareans or any very internal, not necessarily muscular, but internal tissues that are softer. And particularly speaking to cesarean sections and C-sections, I did a lot of targeted research later on where I was able to find that maternal mortality across the world, due to not being able to access sutures like this, so we're having maternal deaths due to complications from hemorrhaging, are unable, the doctors aren't able to help these patients because they don't have sutures in order to fix them on the inside, or they don't have dissolvable sutures, so the risk of reinfection after they take out the sutures, or even in it's just an awkward spot to do sutures in anyway. So I wanted to particularly focus on maternal deaths and maternal deaths relating to not being able to have those dissolvable sutures that are so necessary. So I did some research on my slide here. It says that the maternal mortality ratio was 2,100 per death for 100,000 live births in Sierra Leone. Obviously, this is a horrible fact. We think that in the 21st century, the maternal deaths and infant mortality is way behind us and way past in the 16 and 1800s, but this is still a prevalent problem today, and this is something that could be readily fixed with the availability of obviously more sanitary procedures, but also with the implementation of dissolvable sutures that are able to help these women and prevent them from having these complications and these hemorrhaging and any complications relating to infection after surgery after giving birth. So for increasing the availability of cesareans in women across the globe is very, very important. So this project is seeking to address that and seeking to find an alternative to commercially available dissolvable sutures. so that we can help those in impoverished countries and use science to help and figure out ways we can help people, which is really cool to me. So I looked into a bunch of different suture materials. Obviously, so commercial suture materials are often made of PLA, PGA, or catgut, which is literally they take the intestines of animals, they dry them out, and they stretch them out, and they create this kind of fiber. So obviously I'm not using those methods. They're very complicated, very expensive, and not possible for someone to do at home. Also, there's ethical problems with catgut, and it's really interesting. So I ended up looking at different biocompatible materials that are typically used in the body, and things that are super biocompatible. So I had two options. I was looking at gelatin at first, but I realized that that wasn't necessarily going to work super well. The collagen and the way that the collagen cross-links with gelatin is very easily able to denature inside the body at around 37 degrees Celsius, which is the same temperature, internal temperature of the human body. So the fact that you would put the sutures in and then upon closure it would completely dissolve, it completely renders this ineffective. So I looked at sodium alginate instead, which is actually commercially used as popping boba pearls. It got super popular, I think, about a year ago. And it has been used in many biomedical applications, drug delivery, tissue scaffolding in particular is what I looked at. It has been studied and shown to be biocompatible, non-toxic, non-immunogenic, so it's not going to spark an immune response with your body. It can be stable, so one of the research projects I looked at was using it as a tissue scaffolding, and it lasted for about 6 weeks in the body, which is very, very good for a suture. That particular scaffolding was mixed with the whole other materials, so potentially this could be a lower time as well, and that can be adjusted depending on the needs of the actual suture. And also, it is really cost effective. It's very cheap. I bought mine online. You can get it in stores. It's commercially used in food, so it's not hard to access whatsoever. It's derived from brown seaweed, which is very, very common, very easy to find, and the process of making alginate is also quite cost effective. So once I determined that I was going to use alginate, I came up with a procedure, mostly through trial and error, to be honest, of how to make the suture thread. One day I kind of got lucky. I left this like a string of the alginate on the counter, forgot about it. Next morning I came and I'm like, whoa, this is a piece of thread. This works so well. This is exactly what I was going for. So that was a really cool moment. Once I figured that out, I decided to manipulate the concentrations of the alginate, and I wanted to see how that would affect tensile strength. So I did a lot of experimentation with tensile strengths of just like standard tensile strength. I wanted to test tensile strength with a knot in the alginate, and then I also tested tensile strength after I've hydrated the thread in water. So from these experiments, I was able to determine that a concentration of about 1 to 2% of alginate per percent by mass of alginate was the best alternative and provided the strongest amount of withstanding for the force before breaking. So that was one of my conclusions. So ultimately, I was able to find that alginate sutures are definitely a viable alternative. Some further work would need to be done, mostly on how to make it a little bit stronger. I looked into some research articles, and people have talked about adding collagen, other like substrates, and any other binding agents to help the alginate stick together better. I also think that my methods for measuring tensile strength could have been better. I didn't use a force meter. I calculated force using the mass that it was able to withstand before breaking. I think having more refined ways of measuring tensile strength, maybe with one of those tensile machines, could be definitely a further study and a limitation and something that could be improved upon. Also, something that could be further studied was the application of alginate in polymers for the biomedical industry. I think it's a really interesting concept. I think it's a really interesting material and a really interesting polymer. And I think that it could go very, very far. So anyways, thank you for listening, and have a good day.